Welcome to the third lecture, and the topic is origin of electrode potential. We have studied about components of galvanic cells, mainly four components: anode and cathode. These are the electrodes. The electrode at which oxidation occurs is known as anode. The electrode at which reduction occurs is known as cathode. Electrolyte will act as a conducting medium. Salt bridge will help to maintain the electrical neutrality in the cell. Inside the galvanic cell, chemical reaction will occur, and due to the chemical reaction, electrical energy produces, and electrical energy production leads to electromotive force or cell potential, which can be calculated using the formula cell potential of the galvanic cell equal to cathode electrode potential minus anode electrode potential. This equation suggests that the cell potential is the difference in the electrode potentials of cathode and anode. This indicates that each electrode, cathode has its own electrode potential and anode has its own electrode potential, and their difference will give you the cell potential. So now we got an idea that individual electrodes have their own electrode potential. We have to answer two questions. First, does the potential exist in electrodes when they are part of the galvanic cell as well as when they are staying alone? We studied electrodes have their own potential. Now, first question, whether that potential belongs to them when they are part of the galvanic cell as well as when they are staying alone. In both these cases, whether the potential exists in a single electrode. First question. Second question, how the potential in the electrode originated. What is the reason behind the formation of electrode potential in a single electrode? To answer these questions, we have to take only one electrode. That means only one metal rod dipped in its own solution. For example, here you can see zinc rod is in its own solution zinc sulfate. So zinc sulfate contains zinc ion, which is an ion of the same metal, that is zinc. Here you can see a drawing of a single electrode. A single electrode means one metal rod dipped in its own solution. For example, here zinc rod is in zinc sulfate solution. Zinc rod, it is solid and it contains only zinc atoms. Zinc sulfate solution contains zinc ions, and it is now in liquid form. So zinc ions are in solution, zinc atom is in the metal rod. In addition to zinc ions, sulfate ions are also present in the zinc sulfate solution, as well as the water molecules that you used to prepare zinc sulfate solution. Now, if you dip zinc rod in zinc sulfate solution, what are the possibilities? Whether any reaction will happen or not, that we are going to check. First, the zinc atoms in the zinc rod has a tendency, I will call it as tendency, to release two electrons and becomes zinc ion. Zinc atoms in the zinc rod has a tendency to release electrons to become zinc ions. If it becomes zinc ion, ions cannot stay in the metal rod. What they have to do? They have to come into the solution. So first tendency, zinc atoms in the zinc rod have a tendency to release electrons and become zinc ion and go into the solution. So this reaction, if you see, this is a release of electrons. Equation involves release of electrons. Release of electrons means oxidation reaction. Oxidation reaction. So the tendency to become oxidized, the tendency of oxidation, we call a name, that is oxidation potential. So the single electrode, that is zinc dipped in zinc sulfate solution, in which the zinc atoms in the zinc rod have a tendency to release electrons and become zinc ion and go to the solution. This reaction is oxidation. This tendency is known as oxidation potential. Now next question, whether this reaction will happen or not. Potential and happening, both are different. Here potential is there, tendency is there, but can it donate electrons or can it release electrons and go into the solution? Answer, no. Even though there is a potential for zinc atoms to release electrons, that reaction will not happen. I will give you an analogy to explain this. For example, I want to donate 1,000 rupees. So I have a tendency to donate money. But if nobody is accepting money from me, then even though I have a tendency to donate money, I can't donate. So donating money is a process, is an event. Tendency of giving money, that is not an event, that is not a process. So even though I have a tendency to donate, I can't donate. Same thing here. Here, zinc has a tendency to release electrons and become zinc ions and going into the solution. That potential is there, but it cannot undergo this reaction. The reason, if zinc is releasing electrons, somebody should be there to take that electron. So nobody is there to take that electron. That's why zinc cannot undergo oxidation itself, even though it has a tendency. Like the analogy, I have a tendency to donate money, but nobody is accepting that money. So I cannot donate money. But tendency is there. And that tendency, we call it as oxidation potential. Now, another tendency is this. Zinc ions in the solution, they have a tendency to accept electrons and becomes zinc atoms. So who is having this tendency? Zinc ions in the solution have a tendency to accept electrons and become zinc atoms. Zinc atoms cannot stay in the solution. What it has to do? It has to deposit on the zinc metal rod. Always like this. Atoms will go into the metal, ions will go into the solution. So the second tendency is for the zinc ion in the solution. It has a tendency to accept electrons and become zinc atom. If it becomes zinc atom, then it has to deposit on the zinc rod. See this equation. This equation involves acceptance of electrons. So this reaction is reduction. So that tendency of reduction, we call it as reduction potential. So how many potentials are there? Two types of potential, two types of tendency. One is oxidation potential, that is for the zinc atom in the zinc rod. Second tendency is for zinc ions to accept electron to undergo reduction, and we call that potential as reduction potential. Whether this reaction will happen or not, this reaction is also not going to happen in a single electron. The reason, in order to undergo this reaction, somebody should give 2 electrons to zinc ion. Somebody should give 2 electrons to the zinc ion. Here nobody is there to give electrons, so zinc ions cannot become zinc atoms. It's like I need 1,000 rupees. Imagine in another situation, I need 1,000 rupees. So I have a tendency to accept money. But if nobody is there to give me that money, even though I have a tendency to accept money, I cannot accept. Understand? So this potential is known as reduction potential. So how many potentials are there? 2 potential. One is oxidation potential, one is reduction potential. Whether any one of these reactions will happen at a faster rate? No. Right? If first one is to happen, then 2 electrons somebody should accept. If the second one is to occur, then 2 electrons somebody should donate. So both these won't happen. So we call this the zinc rod. If you dip it in zinc sulfate solution, there won't be any change. And if there is no change in a chemical reaction, we call it as it is at equilibrium. We call it as equilibrium. So here, no change in the concentration of zinc ion, no change in the number of atoms of zinc. Clear? Now onwards, instead of reduction potential, I will use the word electrode potential. I will use the word electrode potential. So actually electrode potential is reduction potential. So 2 tendencies: to get oxidized, we call it as oxidation potential. Second one, to get reduced, we call it as reduction potential. Another name for reduction potential is electrode potential. Now we will study how the electrode potential in a single electrode is originated. What is the reason behind the origin of electrode potential? For that, we are taking the same example, zinc rod in zinc sulfate solution. It's a single electrode. Zinc rod contains zinc atoms, and zinc sulfate solution contains negatively charged sulfate ion. We call it as an anion because it carries negative charge. Zinc ions, we call them as cations because they carry positive charge, and they are represented using this symbol. Water molecule, which is there in zinc sulfate solution because we prepared zinc sulfate solution by dissolving zinc sulfate in water. So 3 types of ions or molecules present in zinc sulfate solution: sulfate anion, zinc cation, and water molecules. As per Helmholtz, this famous scientist, all metals have a tendency to absorb negatively charged particles. The reason, in a metal, the surface will have a charge density creation which attracts negatively charged anions. That means the charge creation or the charge density, very small charge density creation is of positive charge in metals. So all metals have a tendency to absorb negatively charged anions. So zinc sulfate solution contains numerous number of sulfate anion. Among those sulfate anions, some of the sulfate anions will move towards the metal rod and get absorbed on the surface. So I am drawing the adsorption of anions, that is sulfate ions, on the surface of the zinc rod. Be careful, these ions are not reacting with the zinc rod, just absorb. Now you got a layer of negatively charged particles. You can see now a negatively charged particles of anions is created on the surface of zinc rod, and we call that layer as inner Helmholtz layer. And it is negatively charged. Now you got a layer of negatively charged particles. Obviously, that layer will have a tendency to absorb positively charged cations. So in the zinc sulfate solution, we can see we have positively charged zinc ions. So what will happen? Among the zinc ions present in this zinc sulfate solution, some of the zinc ions will get absorbed on the negatively charged inner Helmholtz layer, because opposite charges, they attract. So I am representing the zinc ions. Zinc ions which adsorbed on the surface of the negatively charged cations. When cations are getting adsorbed on the surface of anions, those cations will be solvated. That means water molecule will be there along with the positively charged cations, or we call those cations as solvated cations. The solvation term came because of the water molecule is the solvent. So we got now a layer of solvated positively charged cations. We got a layer which consists of positively charged solvated zinc ions, and we call that layer as outer Helmholtz layer, and this layer is positively charged. How many layers it got formed? 2 layers were formed. One is inner Helmholtz layer, which is a layer consists of negatively charged sulfate ion. Just near to that layer, a positively charged layer formed due to the solvated zinc ions. Now the remaining portions in the zinc sulfate solution, there zinc ions, the remaining zinc ions will be there, remaining sulfate ions will be there, but one difference, the concentration of the ions will be lesser compared to this area. So here also we will get zinc ions, sulfate ions, water molecules, but this area now it is rich in charged particles or ions. This area is comparatively less concentrated in terms of sulfate ions and zinc ions. You know that some of the zinc ions moved into this area, some of the sulfate ions moved into this area. So the number of zinc ions and sulfate ions reduced in this area. So we call this area as diffusion layer. We call this area as diffusion layer, which contains zinc ions, sulfate ions with lower concentration. Now, we can see that two layers are formed, and those layers are of different charge, and these layers are separated by a small distance. Now, as per the electrochemistry, if you have two different layers or areas which contains opposite charges, and if they are separated by a distance, then potential will develop. So this potential is due to two differently charged layers. So there is a double layer, and this double layer is due to their different charge. So we give a name for these layers as electrical double layer. So electrical double layer contains one inner Helmholtz layer and one outer Helmholtz layer. Both layers are having different charge or opposite charge, and they are separated by a distance, so potential will develop. This is the reason why a single electrode gets its own potential. You can also identify the potential in this area will be higher compared to the potential in diffusion layer, because diffusion layer contains less number of or less concentration of zinc ions and sulfate ions. Rather, in this area, this inner and outer Helmholtz layer, the charge of the concentration of the charges are high. So if I draw a graph, potential against distance from rod, potential will decrease. Why potential is decreasing? Because the concentrations are decreasing. Up from here to here, the decrease will be a linear decrease. From here to the inner edge of this container, zinc sulfate container, then the decrease will be exponential. That is the only difference in the decrease. Actually, it will decrease from the rod to the inner edge of the zinc sulfate solution. From here to here, the decrease will be linear. After that, decrease will be exponential decrease. Now we study why potential is formed on summary of this session. Now we have answered two questions which were asked at the start of this session. We answered this question: does the potential exist in electrodes when they are part of the galvanic cell as well as when they are staying alone? We answered the question for how the potential in the electrode originated. So both the questions which were asked at the start of this session is answered now.